Okay, so so anyway, you guys have all been exposed to stress and strain a little bit in your past work on structural mechanics. Um, uh, However, you're going to learn quickly in this class that it's a little bit more complex than what we have perhaps presented it to you. Now, the most simplistic description that you've seen before is the one that's shown here on the screen. That is, we take a resultant force and we divide it by a reference area over which that force applies. And this is what you've likely seen as our description of stress in past classes. Now, of course, what we're looking at here is a normal resultant force, so it's pulled normal to the surface that's exposed. You've probably also seen shear stress, which we'll introduce more fully in a moment. But this, again, very common description of stress. Now, what's interesting about this is that we're assuming, the way we've defined this, that this axially load-carrying member actually has a uniform stress over the cross-section. That turns out to not be a great assumption, in fact, in a lot of our structures. Let me introduce you to a new way of envisioning what stress represents. The image that I've presented here at the left, I like to refer to this as my stress potato. You take an arbitrary volume. In this case, I've drawn it to be sort of in an unusual shape. The body, we're going to call it a body in this class. So that body then is has external surfaces and internal surfaces. I don't know how well you're able to see my mouse, but here I'm drawing a circle. That is the external surface, including this dotted line over this three-dimensional body. And then what I have represented here in the middle is an exposed internal surface. So what we're doing is we're imagining that this body has been cut, at least cut in an imaginary sense. It now has two internal surfaces, which amount to one plane. We've got the surface that you can see that you can see and is exposed with the normal that you see drawn here in red. Of course, if we were really taking a cut on this system and we had separated it into two bodies, there would be another surface with a normal pointing in the exact opposite direction of this on the other exposed half body. But that is what we're doing. So we're taking an imaginary cut in some sort of arbitrary body, in this case represented by my stress potato. We've exposed an internal surface, and that surface now can be described as having a surface normal. Now the resultant force over this entire area, that is the sum of all the stresses times their differential areas. So really those are differential forces. Those differential forces are all vectors. You sum them up by multiplying them by their area. And what you get is a resultant force, here shown by the vector F, which I will circle here. It's obviously a blue vector. So that now is an internal resultant force over an area that was exposed by this imaginary cut. However, this imaginary cut that we took was entirely arbitrary. There was no reason to choose the one that we selected. We could have made cuts in other planes, exposed other internal surfaces, and had we done so, we would have had different resultant force vectors. So that's an important observation, just that we could have made other cuts in our exposing of internal surfaces in the body. Now, we also have to recognize that the loads pass through the body without concern for the plane of observation, meaning they don't really care which way we're pretending that this body has been cut in half. They don't care how we've exposed internal surfaces. They just recognize these loads that are passing through, they recognize that they pass through the body in an equilibrium sense. Consequently, if we expose different planes, the different planes feel different intensities of stress. I'll show you a little bit more about that on the next slide. We also need to recognize that the area of this cutting plane really needs to be associated with the vector that defines the plane. Okay, we've defined a normal vector for this imaginary cut, and that normal vector now determines what area is present. If we had chosen to use another area, we would have, or another cut, we would have had a different area. So we're going to now define our area as a vector. You can see vector represented by the underbar here under A. A is equal to the area A. This is a magnitude now dotted with a normal vector. Okay, so we recognize the area changes with the normal vector selection. This is the internal plane selection. We recognize that the forces that are passed across that plane themselves are also something that varies, according to the plane that we choose. So both the magnitudes and the areas change as a function of the exposed internal surface in our imaginary cut. Okay, now the last thing we need to recognize is this cut that we've made is arbitrary, and we can make further cuts. In fact, we can cut ultimately down to a very small differential area within the body. That differential area then has a differential force vector associated with it that has normal and shear components. I didn't mention the normal and shear components previously, so there's your normal, there's your shear. So in the end, what we've done is we've taken a body, a structure, we've loaded it. Loads are passing through the body. We imagine taking cuts within the body, and by doing so, we expose internal surfaces that have force resultants on them. We can do that in the limit of going to a differential area, a very small area being exposed that has a differential force. And through exposing these differential forces and differential areas, we ultimately compute this complete description of stress. Let me take you to that mathematically now. So assume we have this differential area. Now I'm going to call it delta A of the internally exposed surface on this imaginary cut. And of course, it has a corresponding differential force. We can define something called the normal stress magnitude. We're going to reference that magnitude with the symbol sigma. And we're going to define sigma, this is the stress, normal stress, as the limit, as the differential area approaches zero, of the change in differential force divided by the change in differential area. Really, this is a derivative. It's dFn dA. It's the derivative of the normal force with respect to the area. And we're ultimately going to call this a component of a vector. That vector is going to be represented by the letter T. We're eventually going to call that a traction vector. So Tn represents the normal component of stress on this exposed surface, and ultimately it comes down to being a derivative. You can think of it as a limit as the area changes of how much the force changes. Similarly, we can define a shear stress magnitude. In this case, we're going to use the symbol tau. And in the limit as delta A goes to zero of the shear force component, its change over the differential area change, which amounts to being a derivative. So this is approximately equal to dFs dA. we're going to again call that a component of a vector, in this case, the traction vector, T sub S, the shear component of that vector. All right, I'm going to pause for just a moment and take any questions. I know this is starting to perhaps be a little bit more complicated than you've seen in the past. All right, I'm not seeing any questions in the chat window. I
have a question.
Here, I do see some now coming through, some questions. Yes, who is that? Go ahead.
Why is it that a dot product is used if the resultant of a dot product is a scalar, but here we have the definition as being a vector?
Okay, yeah. So I guess it's not entirely clear what you're asking. So here the area is a vector area, which is a magnitude times a vector direction. This symbol here, okay, so representing dot, since this is not a vector itself, this is just a multiplication sign. Is that ultimately the question, David?
Yes, thank you.
Yeah. Yeah, thanks for asking that clarifying question. That maybe is a notational change that I should make on that particular slide. I agree that it's confusing the way I represented it. Okay, so I mentioned that each of these things, so we had a shear component. Let me go back to our stress potato again. So the resultant force had a shear component. It was a vector. It had a shear component, and it had a normal component. Hence, our traction vector also has a normal component and a shear component. So I will write the traction vector here, T, as being the sum of the normal component and the shear component. And then ultimately, the resultant force is the area in magnitude multiplied by the traction vector at that point. Now, what I think can be a little confusing is this whole description that I gave of the magnitude of that vector being now a function of the plane that we chose. Okay, we're choosing a normal vector, and the magnitude of that force is now a component. You know, the components, I should say, of that force vector are now a function of the plane that we chose. So I'd like to show you this slide where I think it becomes a little bit more clear exactly what we're doing. Okay, I'm showing you now an axially loaded member where I have on the left-hand side applied a uniform stress. Now the rest of the member is not drawn here. I'll just draw it momentarily. Okay, so of course we could have done exactly the same thing on the right-hand side. Now I've taken my imaginary cut, and what you see here in black and then dotted lines indicating this imaginary cut that I've made on the internal surface of my axially loaded member, I think it's relatively easy to recognize that equilibrium requires there to be a reaction force. The force on the left-hand side is this uniform stress times whatever area was present here. So we're going to assume it's a unit area. So it's the integral of this pressure gives us a force that is going off to the left. And on the right-hand side, we have a force vector resultant that is in magnitude large enough to offset that same force on the left-hand side. Now, I mentioned I can choose to make my cut on any plane. I didn't have to choose the plane that was normal. So in this axially loaded member, I can still choose a plane like I have in this second portion of the image that is at a different orientation with respect to the sort of axial direction of this axially loaded member. So here I've now made a cut that has a 45-degree plane to that axial direction. Now, of course, the left-hand side of this has not changed. So what do we know? We know that the reaction force on our now newly exposed surface is identical. So the length of this vector here, this blue vector, and this vector here are identical. However, relative to the surface up here on top had a normal that was in the same direction as that vector. Whereas here on this 45-degree plane, the components of this reaction force vector, this integrated internal load vector, it has to have components, one of them being normal, I'm highlighting now, and one of them being in a shear direction relative to that surface, which I've highlighted. So the magnitude of the normal component has changed from here to here. The reaction vector overall has not changed, but the magnitude, the component of that vector that's associated with the normal direction to our internal surface, that magnitude has changed, as has the shear vector. And then last but not least, there's no reason why I couldn't have made a cut, in this case horizontally, so I've exposed the internal surface along the entire length. Now, of course, we have a normal vector that's in our y direction, we'll call it, for lack of a better descriptor, so in the vertical direction. Now, if you were to take and calculate internal reaction forces on this surface, you can see that the left-hand side is now balanced by stresses that are present at the right-hand side. And so actually on this exposed surface, there is well, in fact, still a reaction, or I should say a resultant vector. It just happens to be of magnitude 0. So if we took this cut, we'd have the largest normal component. In this cut, we have somewhat less of a normal component, but we also have a shear component. And in this cut, we have no normal component and no shear component. So this is a pretty simplistic description that sort of illustrates in ways that I believe everybody can understand how the normal that we choose now influences the traction vector that comes out of that normal selection. Okay, now what you have heard of as the stress state, and we've, up until this point in your career, maybe have just referred to this as sigma, or maybe if we got a little bit more advanced, we said we have normal sigma and shear tau. To get the complete description of the stress state, now we need to recognize that we must be able to describe a resultant traction vector on any surface that's exposed within the body. Okay, so I'm going to pause again for questions. I hope I might get a few.
So in the third example, you say that there's 0 shear stress. Or
Yeah.
like when I look at it, I would think that it would be like 100% of the stress is shear.
Okay, so that's a good question. Can you tell me who was asking that?
Caden Allen.
Okay, thanks, Caden. So as we've now exposed, so we're looking now at the third one. We've exposed this internal surface. Okay, we need to do the sum of all forces on this internal surface. So I'm going to take the bottom half. We see that we have a uniform stress here on the left-hand side times an associated area. If we look at the right-hand side now, because there's no cut on that, that interrupts the flow that goes through here, now we have a uniform stress on the right-hand side, and it has an associated area. So this area times this distributed force plus this area times this distributed force, these two things identically balance each other out. So even if I drew a vector here, we would know that the components of that vector actually have to be 0, both in the normal direction and in the shear direction. So does that make sense, Caden?
So it's more of, it's about whether you interrupt the flow of the stress.
Well, it's more applying equilibrium, and you can think about it as interrupting the flow of the stress. We will talk about flow as load is flowing through the structure. The reality is that you can actually think of it as a flow if you so choose to, but really this is just application of equilibrium. You know, you need to, even though, so what we're doing here is we're saying all of the forces on this lower body, and I'm now going to draw a box around this entire body, have to be in equilibrium. Okay, we know the boundary condition here, we know the boundary condition here, we know the boundary condition here on the bottom's got to be 0, and if we sum up all of those forces, the boundary condition on the top, it also contributes to the forces, and it just force balance drives it to 0 in this case.
All right, thanks.
Okay, so I hope now I have convinced you that these internal planes, these internal imaginary cuts that we can make, each of them has an associated traction vector as loads pass through the body. Now, the vectors themselves, I'm going to claim, must be related to a more fundamental set of quantities, which from now forward we will refer to as the stress tensor. Okay, I want you to stop thinking of stress as a magnitude and start thinking of it as a tensor. Now, what do I mean by that? Okay, consider that we took that stress potato and we began to take imaginary cuts. I need to start bringing props with me to class. I guess if this were a normal lecture, I actually would have brought props with me, and I would have held them up and sort of hand waved with them a little bit and said, all right, let's imagine cutting it in this surface. And now let's imagine cutting it in this surface, and imagine cutting it in this surface. And you continue to cut until you get a differential parallelepiped. So you're getting a small cube with parallel sides. This is a very small portion, a differential volume interior to our stress potato. So the sides, it has of length dx in the x direction, it's dy in the y direction, and dz in the z direction. We refer to this small differential element as a parallelepiped. We're going to choose to conveniently align these parallel faces with a coordinate system defined by x, y, and z. So it's a Cartesian coordinate system in this example. Most of the work we'll do this semester will be in Cartesian coordinate systems, but eventually we're going to move away to different coordinate systems. Now, we've exposed, by taking these imaginary cuts, actually this parallelepiped has 6 internally exposed faces, and load is passing through this cube, through the faces of the cube. You can think of the external tractions of the cube as being the boundary conditions on the cube with load passing through the cube. So looking just at one face, I'm going to call it the x normal face. So plus x direction. We have now on this face 3 components of a vector. We have a normal component. We have a shear component that's oriented with the y direction. We have a shear component that's oriented with the z direction. Now, this is really no different than what I had done here with our, in this case, we would have only had 2 dimensions because of the way it was drawn. So we would have had an x component and a y component, or with the exposed surface of the one in the middle, we could have defined our coordinate system to be x in one direction, y in the other direction relative to the normal. And again, we would have x and y components. But when we move to 3 dimensions, of course, now we have 3 components rather than 2. So on this face, there is a traction with 3 components. Again, it's aligned with the coordinate system. We have to look at how we name our components And by convention, we name them associated with the normal direction of the face, and we use subscripts. So let me go back to this image for a moment. The first subscript is the normal direction for the face. So on this particular face, they are all x normal faces. All of these components are associated with that face, the x normal face, positive x normal face. The second subscript is now the direction of the component force or component traction. So we have an x normal face with an x direction component. We have an x normal face with a y direction component, and we have an x normal face with a z direction component. Now I've drawn the arrows associated with the assumed component directions, and we'll eventually let minus signs switch those directions around if that is appropriate. So going back to this slide with the text on it, again, we have a normal direction. The first subscript describes the normal direction of the face. The second subscript describes the direction in which that traction acts for that particular component. In all of these cases, the components of stress have units of force per area. And we'll call these the components of the stress tensor. Now, by convention, a positive stress is defined when that stress acts in a positive direction on the positive face. Or alternatively, we'll also call it a positive stress when the stress acts in the negative direction on a negative face. Let me see if I can draw that for you. I'm doing this with my mouse, so forgive my less than stellar artistic ability. Here we have a normal face that's positive in the positive direction. So here's our positive normal. If we happen to have a normal associated, if we had chosen to make a cut where we had a normal that was facing in the negative direction, if the component of force was in the negative direction, we still cancel the negatives and call it positive. So either of these would be called, by convention, a positive stress. Now, similarly, so I'm doing this in 2 dimensions. Here's my positive normal. If I have a force component, that is a traction component in this direction, it is on a positive face in a positive direction. In this case, the positive y direction. So if we call this sigma xy, it's positive if it's oriented this way. If it were on a negative normal face and it were in the negative direction, this would also be a positive sigma xy. If it were on the negative face but instead went in the positive direction, then that would be negative. Okay, I hope all of that's relatively easy. If it's not, feel free to interrupt me as we move forward. Now, to make this even more general, as I stated, we have 6 faces. So we have a positive x normal face, we have a positive y normal face, we have a positive z normal face. By arguments that we made a few slides ago, each one of those faces has its own traction vector. So the one that I've already shown you is x, xy, xz. We have one. Let me view this image so that it's a little bit easier to see, perhaps. I don't know if that helped at all. We have in fact, I don't think it helped at all. We have the y face, so it's on a y positive y face direction in y, so the normal stress is called sigma yy. Here we have sigma yx, so it's in the normal y normal direction, but the traction vector's creating a force in the x direction, and similarly z. And then last but not least, of course, we have the z normal, and then zy and zx. So these are actually three different traction vectors, which I've written down here. So the traction on the x face is sigma xx times the unit vector in that x direction, which we'll call I, sigma xy times the unit vector in the y direction called j, and then sigma xz times the unit vector in the z direction called k. Three stresses, or three components of stress for each traction vector, three faces. So we actually now have 9 stress components: xx, xy, xz, yx, yy, yz, zx, zy, and zz. All of these are still vectors. Again, the components have magnitude of force per unit area. It's a component times a direction, component times direction, component times direction. Okay, so at this parallelepiped, this is a point in space. It's a differential volume that we've imagined taking that full body and taking successively smaller and smaller cuts until we've exposed a parallelepiped or a cube interior to the body of the load-carrying member. There are 3 different planes: an x normal, a y normal, and a z normal plane, and it has 3 different traction vectors totaling 9 components. The 9 components now can be written more succinctly in a matrix format that I'm showing here. And we're going to now begin to refer to this as a tensor at the point. That tensor is called the stress tensor. So the stress tensor, previously you've thought of stress likely just as the normal component, 1 magnitude or maybe 2 magnitudes. You had some normal component and you had some shear. Now we recognize that in a more general sense, we have to have 3 3 traction vectors, 9 components. So stress is actually, in the most general sense, a 9-component tensor. Now, what am I saying? I'm saying tensor. Note, I'm not saying vector. We'll get into the details of that in just a moment. Very briefly, though, instead of having just one direction associated with it, we actually have 2 subscripts or 2 directions. Two unit vectors ultimately define different components of stress. Now, this is a bit redundant to what I've already said. Each stress component is named using 2 subscripts. The first describes the normal direction to the face. The second describes the direction in which the component acts on that face. So more specifically, we can refer to this as sigma ij. We're using 2 Latin indices as subscripts. So it's stress on the plane I in the direction j. Sigma xx is a normal stress. So when you see a repeated direction, we now recognize that as what we used to think of as normal stress. We still think of it as normal stress, but now we recognize there are actually 3 normal stresses: xx, yy, or zz. Now, periodically, you might just see this written as sigma x, or even more greatly simplified and written as sigma if it was just a uniaxial stress present. However, I don't particularly like those notational schemes. I think they drop some of the rich value that comes into recognizing that there's actually 9 components of this tensor. As I also had previously alluded to, so now if we have 2 subscripts that have different letters associated with them, so xz, by the way, we're going to not strongly differentiate between tau xz and sigma xz. Those things are functionally the same. So we have xz, we have xy, we have yz. Those are now called shear stresses. The reason why you have seen tau written at times in your past experience is because usually when we're thinking about a two-dimensional stress field, then we might just call them sigma representing the normal and tau representing the shear. But in this class, we're going to largely drop that representation of tau, with one exception, which I'll allude to later in the semester. And we're just going to call them all sigmas. So they're all uniformly sigma with two subscripts. And then if it's xz, yz, or x or y, xz, yz, or xy, those are the shears. And the positive stresses are what I have shown. Okay, questions about that? Okay, so now I called this a tensor, and I'm sure you've maybe heard that word once or twice before, maybe not put a lot of thought into it. So a natural question is, what is a tensor? A tensor simply describes a linear relationship in a geometric space where you have components and they're associated with directions. So a vector is actually a tensor. So you guys have heard that word many, many times. A vector is a magnitude and then a direction that it's associated with. When we talk about tensors more generally, we need to now think in higher dimensions. So in this example, we actually needed two directions in order to define what component we're talking about. We had an XX, two directions. We had an XY. So this is what we would call a second rank tensor. Stress is a second rank tensor. So if you hear me say the word rank, the rank of a tensor describes the number of directions that must be assigned when describing that quantity. So the simplest tensor is actually a scalar. It's a rank 0 tensor. It's a magnitude with 0 directions. Now, one way to think of it is how many components exist on a scalar. Well, it's 1. In this case, it's 3 to the power 0. So a scalar is just represented by one magnitude. Vectors, which we're all quite familiar with, in this more general terminology is called a rank 1 tensor. Again, it has a magnitude and one direction. So it has 3 components in a 3-dimensional space, 2 components in a 2D space. Most of the work we'll do is in a 3D space. The word that we would use to describe a rank 2 tensor would be to call it a dyad. I often just forget that word and instead call it rank 2. It has a magnitude and 2 directions. So there are 3 to the power 2 components. That's, of course, 9 components. We can go a step higher to a triad, which is a rank 3 tensor, magnitude in 3 directions. 3 to the third is 27 components. This can be generalized to saying a rank n tensor, which is a magnitude in n directions. And so that's 3 to the n components. Turns out in structural mechanics and fluid mechanics, we're going to actually encounter rank 4 tensors quite frequently. So 3 to the power 4 would be 81 components. And we'll see that in this class. So this word tensor, what is it? Well, just in your mind, think of it as a generalization of a vector to a higher number of dimensions. Now, without going into all the details, I will mention, mathematically speaking, that a tensor follows certain transformational rules. These are essentially mathematical rules that govern how a tensor can be calculated in different coordinate systems. Now that's something that's not unique. You know, you've experienced that with vectors. If I were to hold up my hand, and actually I have to hold up both hands. I'm going to hold up. Now I have to be thoughtful about this because I recognize that you guys are seeing me from a different direction. So I'm holding up my right hand so that my coordinate system, X, Y, and Z in a Cartesian coordinate system defines the right-hand rule. Now, I encourage you guys to think about this because I think when it projects the screen, it may project it a little bit differently. So if I take a vector and I put it in this three-dimensional space, if I reorient my coordinate system, so here I have my thumb is aligned with that direction. I know this is quite difficult for you guys to see, but I'm going to do my best. Here my index finger would be aligned with this direction. Here my middle finger would be aligned with that direction. As I reorient, the magnitude of the components in the X and Y and Z directions change. The vector never changed. So its magnitude was preserved irrespective of that transformation that I did as I observed it from different coordinate directions. Same thing happens to stress. The magnitude of the stress, in some sense, needs to be conserved as you observe it from different coordinate systems. So it's not, in fact, higher rank tensors, second order tensors must conserve magnitude and more. We'll get into what that more is as we go forward into the next lecture. Okay, are there any questions? All right, now we've talked about this traction vector. We've talked about the stress tensor. We related the two of them by examining that parallelepiped, that little cube, infinitesimal cube that was oriented with respect to our X, Y, and Z coordinate frame. However, really to be able to consider traction vectors on arbitrary planes, not directly aligned with X, Y, or Z, we need to do a little mathematics. So that's what I am showing you here with this image. I've got an X, Y, and Z direction in our Cartesian space. That parallelepiped that I had previously, that cube, I'm now imagining one more cut. Take my cube, cut it one more time, and I've defined a new internal plane. That new internal plane has the normal n. Now, in our prior discussion where we were looking at the cube, we recognized that the outer surfaces of that cube had traction vectors associated with it. So now these happen to be drawn on the negative faces, ty on the negative face in the negative direction, tz, again, negative, negative, tx, negative, negative. Our new internal face with the normal n has yet another traction vector, which we're going to call Tn. Now we have tractions, Tn, Tx, Ty, and Tz. We can determine what Tn is, the traction on this new arbitrary plane, from the other tractions. I'm going to highlight that. So the traction plane can be determined from the tensor by passing a cutting plane through the equilibrium element and then ultimately summing the forces. Okay, to really do this, the easiest way to do it is to define a normal. So the normal n is going to have three components to it. We're going to call it Li, M, J, and Nk. Now, it turns out that these L, M, and N are direction cosines. So they're cosine of the angle swept between the N direction and the X Cartesian direction. Cosine of the angle swept between the N direction and the Cartesian Y direction, and cosine of the angle swept between the N direction and the Z direction. So this normal is defined by the angles of the plane that has been cut. Now, as a vector, if the magnitude of the normal vector is of length 1, then you realize, of course, then that there's going to be some constraint on the magnitudes of L, M, and N. The sum of the squares of those magnitudes will have to be equal to 1. None of those individual magnitudes can exceed 1. Okay, this cut plane, now it has a differential area dA. So that's the surface of this internally exposed imaginary cut. So if the cut plane has an area of dA, then we can determine what the areas of the other faces are. So really, after taking it down from 6 external surfaces, making a cut, we now have 4 total external surfaces, one associated with Tx over here, one associated with Ty, one associated with Tz. The area of the largest surface, the one that is the normal N surface, that has magnitude dA. And then just using the direction cosines, we can compute the areas of the other triangular surface. They are dA times L, dA times N, and dA times N. So in this case, we have the magnitude dA times the normal vector dotted with the unit vector. I, j, and k are unit vectors in the original Cartesian frame. Okay, so let me go back to this for just a second where the image is slightly larger. Okay, this now newly exposed subvolume, this differential volume, has to be in equilibrium. So the sum of all the forces on that internal body have to be equal to 0. So I'll put a 0 on the right-hand side, and then I will take the vectors. So we have Tn, which is this vector here, times its area. Remember, its whole area was dA. Okay, I'm going to drop the d because ultimately the differential area would be existing in all of these. So it's the traction vector times A minus, notice that this one's pointing in the positive direction, this one's pointing in the negative direction, so minus the traction vector Tx times its area, minus the traction vector y times its area, minus the traction vector z times its area. The sum of all of those has to be equal to 0 if this element is to be in equilibrium. So from that, of course, we can divide by our area, and we can ultimately get that the traction vector n is the sum of Tx times L, Ty times M, and Tz times N. Again, those are direction cosines. We could equivalently write this as components of a vector. So Tn is going to be equal to Tnx times the I direction plus Tny times the j direction plus Tnz times the k direction. Again, these are subscripts. You recognize this is the n normal face, the component of it in the x direction, n normal face times the component of the y direction, n normal face times the component in the z direction. So this is the magnitude of that component. which now we will see is related to Tx times L. And so in the end, these components are Tnx is equal to sigma xx times L plus sigma xy times m plus sigma xz times n. So this component is all of this stuff here. And similarly, we have a y component and a z component associated with that n normal direction. And they take on these other magnitudes, yx times L, yy times m, yz times n. And lastly, zx times L, zy times m, zz times n. So Nicole is asking, can you explain the negatives on the summing forces again? I sure can. Let me go back to this slide here. In fact, let me go back a few more slides. So what I drew here was my parallelepiped, the positive x face and the positive direction. So the traction vector that was positively drawn on this face was positive. Positively drawn on the y face was positive. Positively drawn on the z face was positive. Then I took this cube and I sliced it. And what remained was the negative faces, which would have had traction vectors associated with them. I didn't draw them here, but they certainly had those traction vectors associated with them on those negative faces, and they would have had components drawn in the negative. In order to be drawing positive stress components, they would have had to be negative on the negative side. Now, going back over here, nevertheless, those traction vectors are vectors. So when you sum them up, they have, in this case with x, it's an arrow pointing in the it's in the negative x direction. So it is a negative force, even though it was components on so it's a positive component now on a negative face. So it's negative. So that's where we got the negative from. So if you're summing them all up, this one's pointing in the positive direction. This one's pointing in the negative direction. This one, although it appears to be pointing in the positive y direction, it's actually pointing in the three-dimensional view as a negative z direction. So this is z direction over here. The force is in the negative z direction. So that's where the negative tz times a comes from. Okay, I hope that makes it more clear, Nicole. All right, I'm going to pause. Is everybody with me on this? So Ron asks, so A is equal to AX equals AY equals AZ. So no, that's not the case. AX, let me go back one slide. Here it was. AX was equal to A times L. So it was the area of the X on the X face was equal to the total differential area times the unit vector dotted with the x direction, which was equal to AL. Similarly, we had an AM and an AN. So, so to correct your equation, it would be, well, it would be slightly different than what you've written. Okay, I appreciate that you guys are asking questions. I do think that that clarifies. I'm more than confident that if one person is confused, that multiple people are confused. So don't hesitate to ask questions when there's a lack of clarity. All right, so now I'm going to just kind of highlight this whole set of equations here. What I've got highlighted in the box can be more succinctly written as, so you see this is three components of a traction vector, nx, ny, and nz. So this is a vector on the left-hand side is equal to something. It's got to be a vector on the right-hand side. I can write it more easily this way. The traction vector associated with the n face, it's a vector, is equal to that 3 by 3 matrix, the tensor dotted with a normal vector. Okay, so this formula is called Cauchy's formula. You recognize the dot product reduces the rank of something. The rank 2 tensor dotted with the rank 1 vector results in a rank 1 vector. It's the dot product. You know, if you go back to vectors, that's how you get magnitudes from vectors, is you dot them. Similarly, if we dot a rank 2 tensor with a rank 1 vector, we reduce the rank by 1, so we get a vector is equal to a vector. Here now the sigma represents those 9 components. The n vector is now the vector that's associated with the face. It's normal to that face, and this is now the exposed internal traction vector associated with that face. Okay, I hope everybody is able to follow along. Any questions out there? I do want to pause regularly for questions. They don't all come through a chat box easily, so if you would like to ask a question verbally, now would be a great time.
So for Cauchy's formula, why is the rank 3, or was it 1? Why does it decrease?
So that is essentially mathematically the definition of the dot product. And you've never probably heard it described that way, although you have used it that way. Let me take you back. In fact, I can draw right here on this screen, perhaps a good way to do it. So if I define an X and a Y coordinate system, and I draw a vector in that coordinate system. Okay, so I'm going to call that vector V, which in a two-dimensional space is going to be equal to some magnitude A times I plus B times J. We can calculate the X component of that by essentially dotting V with I. So you're dotting it, and then this is now a magnitude. It's a scalar value. So in this case, it's A. Really, I could have written this equivalently. So V, this was an equivalent way of writing what we had before, is Vx times I plus Vy times J. This is a scalar. This is a scalar. The combination of the two of them, when appropriately multiplied by the direction vectors, was a vector. So V itself was a vector, but when you take the dot product, you are reducing the rank to a scalar. So similarly, when we had sigma, which was a 3x3 tensor in a matrix sense, you can also just think of it as being a scalar that has 9 components dotted with a 3 components vector. You're going to reduce its rank, and it's going to end up being, so in a matrix sense, this is going to be 3x1 is equal to a 3x3. This is a matrix multiplied by a 3x1. So matrix math, you probably didn't think much of it at the time, but you were working with tensors and you were doing rank reductions when you multiplied these vectors together. Okay, I have to find my place again now. Okay, so here we are. Any further questions? Thanks for the question. I'm not sure who that was, but thank you. Oh, so here's a question from Sarah. So Sarah asks, so the rank is only dependent on the direction. No, it's actually dependent on the number of directions that you need to describe the overall quantity. So stress being a rank 2 tensor, we need 9 components, and each component has 2 directions associated with it. One is the direction of the face, normal. One is the direction of the acting force. So 2 directions necessary to describe stress, rank 2 tensor. Vectors, one. Now, when we say one direction, it's components in that direction, right? So where did my, gotta find my work that I just did. Sorry, I'm a little bit turned around. That must have disappeared. It was on Cauchy's. Oh, here it is. So a vector, each component had one direction associated with it. So AI, BJ, AI, one direction, rank 1. Sigma XX, 2 directions, rank 2. Okay, so you've seen this equation in the box now already. This is Cauchy's formula. In this case, it's represented as 3 equations, 3 tractions, Tx, Ty, Tz. These are vector components. This is going to be now equal to sigma xx times I, sigma xy times j, sigma xz times k. 3 vectors, each having 3 components, one with each direction. Now that's on a arbitrary surface with normal n. So a question is, what is the value of the stress component normal to the surface? Okay, if we're to look back at this image here with the normal n direction, one of the questions we will ask ourselves repeatedly in this course, explicitly or implicitly, is what is the normal component of stress on that face? What is the normal component of stress on this n normal face? All right, so the answer is yes, we can compute it. The stress normal to that cutting plane, we're going to call that stress NN. So NN is the normal, it's actually that traction Tn dotted with the normal vector. So we have here's that rank reduction that we were talking about, right? So we have a 3x1 vector. Tn is a vector. We dot it with a normal, and we'll get the component of that vector in the normal direction. So mathematically, this is going to be as simple as saying after the dot has occurred, L, the magnitude of the direction cosine, times Tnx plus m times Tny plus n times Tnz. And we had gone through and calculated each one of these magnitudes separately on a prior slide, Tnx, Tny, and Tnz. And so when we make our substitutions, the magnitude of the NN component, this is the normal stress magnitude. Now I got to be careful. It is a magnitude at this point because we took a vector dotted with a normal, gives us a magnitude. It's going to be sigma xx times L squared plus sigma yy times n squared plus sigma zz times n squared plus these combinations mn sigma yz plus ln sigma xz plus lm sigma xy plus mn sigma zy plus ln sigma x. Yeah, you don't need me to read it all to you. You see it actually has a contribution from each of the 9 components: xx, yy, zz, yz, xz, xy, zy, zx, yx. Each of the stress components, there were 9 of them, contribute to the normal stress. And how much do they contribute? Well, it depends on the direction cosines associated with the plane that you have cut. Now, what one might ask, why? Why do we care? Why do we care what the magnitude of the normal component of stress is? Why do you go through the trouble of computing it? Well, it turns out that the maximum value and direction of sigma nn will often control the design of the load-bearing member. Okay, if you think about it, as stress flows through a structure, it's most likely to fail, especially if it's a brittle failure where the magnitude of that normal stress is its largest, and it will crack perpendicular to that magnitude, or to the perpendicular to the direction associated with that magnitude. So I don't know how well you can see my hands. If I'm pulling normal, let's see here. I'll try it this way. Okay. My thumb's now representing stress magnitudes, normal stress magnitudes. We're going to pull those apart. Where these magnitudes become the largest, we're pulling the material apart. If it's brittle, it will fail, and a crack will begin to open like so, where the normal stress is maximized. So that's why we would like to be able to compute the stress normal on any cutting plane. Now, since we've computed the normal stress component, we also would like to be able to compute the shear stress component. Okay, we're going to call that stress component NS, and we recognize that since the magnitude of the n component is the sum of the squares, the square root of the sum of the squares of the normal and shear components, we can do just simple mathematical manipulation to say that the shear component is going to be related to the normal component and the planar traction. So the traction itself squared minus the normal component squared, that under the square root sign gives us the magnitude of the shear component. So here, mathematically speaking, sigma ns is equal to tnx squared plus tny squared plus tnz squared. This is the magnitude of the traction minus the normal component squared. So, of course, a natural follow-up question is why? Why do we care about what the shear stress component is? Well, it turns out that it's also quite important in mechanical design. It turns out that material yields, when you've heard of plastic deformation and yield, what's going on at the atomic level is the material is sliding along slip planes, and that is a shear-driven process. So the shear component drives yield or failure for a ductile material. So a ductile material, like most metals, yield based on a shear component of stress. Whereas brittle materials, as I mentioned on the last slide, they tend to fracture, and they fracture associated with normal components of stress. So one of the things that we'll find as we go forward in the class is that the maximum value of the shear stress is related to the maximum value of the normal stress and the minimum value of the normal stress. So we will want to eventually compute both the maximum and minimum values, and then that will give us an indication of what the maximum shear stress is. Now, I haven't taught you how to do that yet. We're going to do that probably next lecture. Okay, again, I'm going to pause for questions. I hope things are relatively clear. Okay, let's go through a couple of quick examples of computing tractions so that you can get an intuitive understanding that this actually works. Okay, not just a descript, I've given you now a description of why it works, but I want to convince you that it actually works out mathematically as well, and that mathematical outcome actually follows your intuition on the matter. So here's an example. Given a stress that I define for you, compute the normal and shear stress on some specified planes. Okay, we're going to use this example that I showed you previously. I felt that that was a fairly intuitive description of the resultant force on a internal surface that we've exposed by taking an imaginary cut. Okay, I'm going to define the stress. Again, we've got a negative face, negative stress here. It's uniform. I'm going to say that it has magnitude 1. And further, I'm just going to assume for simplicity that the cross-sectional area is 1. So this area is 1. This magnitude is 1. And so if you look at all of the forces that are present here, we can define the stress tensor, 9 components, as having magnitude 1 in the sigma xx location. The remaining of these sigma components, the stress components, are all going to be 0 for this example. And what I'm asking for is n and s. So n and s in this case represent the normal component of the traction vector and the shear component of the traction vector on the internally exposed surfaces. So how do we do it? Well, we do it using the mathematics that I've just described. So here's my solution. To compute the traction vector itself, I need to know what the stress tensor is, and I need to dot it with a normal vector associated with some surface. Now, the easiest one, in fact, I don't even have it really in slide form. We'll just do it quickly in our heads. The easiest one is the top one. So the normal vector for the top one is I equals 1, or really L. This is L, M, and N. So the magnitude of the direction cosine. The normal surface is entirely in the x direction. So the normal for that would be 1, 0, 0. And if we put a 1, 0, 0 right here, for some reason, I'm not able to draw it. So if I put 1, 0, 0, we took this dotted with that, we'd get 1 times 1 plus 0 times 0 plus 0 times 0. So you'd get a 1, and then 0 times this and 0 times this. So you'd get 1, 0, 0. And you'd recover the most simplistic form of the traction vector. That is that it has magnitude 1 and 0 and 0 in the x, y, and z directions explicitly. Now we're actually doing the computation for the second one. So for the second one, we need to ask ourselves, well, what's the normal and shear component, n and s, for this imaginary cut? In order to do that, again, we need to define the normal vector associated with that plane. So the normal vector because I've cut the plane at 45 degrees, is going to have a component in the x direction, and it's going to have a component in the y direction. Again, intuitively, we're looking at the vector associated with this direction. Let me draw it for you here. So, if I'm defining this plane and this normal, assuming that that's 45 degrees, it has a component here and a component here, which are in magnitude 1 over root 2 in the x direction, 1 over root 2 in the y direction, if the magnitude of this vector is 1. Now, it's worth also noting that the area of this planar surface is going to be the square root of 2. So it's going to be a larger surface area than when we had the surface area that was straight vertical. That was of magnitude 1. We can see that this one is larger, and it turns out that in magnitude, it has a value square root of 2. So Cole asked, can I return to the normal equation? I assume you're talking about this normal, Cole. Can I move on? I'm going to assume that's what you mean. Ping me back if that assumption is incorrect. Okay, so here's the math. It's pretty simple. Tx, ty, tz. Cole wants me to move back a little bit. Know the one prior to the shear equation. Not sure which one you're referring to. Cole, feel free to jump in and just ask verbally with more clarity what you're asking for. Okay, he says never mind. All right, so anyway, here's our calculation. It's the Cauchy formula. Tx, ty, tz is equal to the stress tensor, represented in this case by a 3x3 matrix, dotted with a normal vector, in this case represented by a 3x1 matrix. And so you can see the x component of that using matrix mathematics is pretty straightforward. It would be the same, of course, with any other form of mathematics. So 1 times 1 over root 2 plus 0 times 1 over root 2 plus 0 times 0. Tx is going to be equal to 1 over root 2 pascals. Now, this is, it has units of force per unit area. The x component, 1 over root 2. The y component, 0 times those. The z component, 0 times those. All right, so we're going to need to sanity check that answer. Hence our Tn. Tn is equal to 1 over root 2 times I plus 0 plus 0. Again, the traction vector is force per unit area, and the total force is now the total area times the magnitude of the traction vector, so this is going to be equal to 1. Cole, I see your question. I'm getting back to it in just a minute. So I want to make sure that this is intuitively clear to you. We have a traction vector that's itself that has a component only in one direction. The other directions are 0. So if I go back and I look at our image, the traction vector is the big black arrow, and it makes sense because it needs to offset the left-hand side that it is only in the x direction. The other two components are 0. That is the y and z components. Now let me get back to Cole. Cole, it's not terribly critical that you memorize this equation. I think this is what you're now asking for. this equation for NN. It's not terribly critical that you memorize that. You're going to find that you're going to move very quickly to doing this using either matrix operations or in what's called index notation. In either case, it's very infrequent that you would use it in this form. This was derived this way so you could see that the normal component has contributions from each of the 9 components, but no need to memorize that equation. So Nicole says, for notation, what is the difference between the square brackets and the squiggly brackets? Really, the way I'm using them, the squiggly brackets are representing a 3x1 vector, and the square brackets are representing a 3x3 tensor, but that's not strict. That's just the way I'm representing them here. It's not critical. You could infer those from the equation if you chose to. If you know what you're doing, you can infer those. The reason to do that is to make it a little bit more clear that we're talking about vector, tensor, vector, although I admittedly am a bit redundant because I also put the vector symbol over Tn and over the normal. So I've kind of made a hybrid notational scheme here where one is a vector. I could actually put 2 arrows over the sigma representing a rank 2 tensor. And it turns out that once you get to more advanced structural mechanics, you're going to drop both of those notational schemes because they're a little bit lengthy, and you'll largely infer what the rank is from how the equations are being used. Okay. It is now 4 o'clock, which means our time has expired. We'll return to doing more examples next lecture. That'll be Thursday. I'll stay on the line here for a little while so that I can take more questions if you have them. Otherwise, I will talk to you guys again on Thursday. Hopefully I'll get some office hours visits Thursday as well. I haven't seen you guys in office hours yet. I imagine that's because largely there hasn't been a real challenging homework set that's come out. But don't hesitate to come in to office hours or make an appointment if you need to. Some of these things that we cover in lecture can be a little bit confusing, and I want to make sure we get them clear early in the semester when they will give you the maximal benefit. So I'll see you guys. I'll hang out here for a few minutes, but otherwise I'll see you guys on Thursday.